Let's use the graph of y equals f of x to solve our next exercise. We have a graph, and in part A, we want to know what are the zeros of f. Well, the zeros are just the places where it crosses the x-axis. So we can see from our graph that it crosses at -2 and +2, and so our zeros are -2 and 2. In part B, we want to find the values of x for which f of x is equal to -1. Now let's think about this terminology. We know that f of x is -1. In other words, the y values are -1. So when y is -1, we want to know what are the values of x. Well, we look on our graph. If you put a line here when y is -1, we can see that it would cross the graph right here and right here. So therefore, the values of x corresponding to when f of x or y is -1, we have two values for x. We have first when x is +1, we have a y value of -1, and also when x is -1, we also have a y value of -1. In part C, it's a similar question. We want to find the values of x for which f of x is -2. So in this case, we're looking when the y value is -2. Well, there's only one time that occurs. Right here at this point, we have a y value of -2. Well, the question is, what's the value of x at that point? Since this point is really 0, -2, then the x value would be 0 when f of x is -2. Let's move on to part D. We want to know, is our function f even, odd, or neither? Well, remember, if a function is even, that simply means that f of -x is equal to f of x for all x in the domain. If it's odd, that simply means that f of -x is equal to -f of x for all x in the domain. There's also another way to determine whether it's even or odd. Anytime a function is even, it's symmetric with respect to the y-axis. And in this case, we can see that our function is symmetric with respect to the y-axis. So we can see that it's even. But let me talk a little bit more about why it's even. Let's look at a couple of different values. We see that f of -2, in other words, when x is -2, the function value is 0. That's the same as f of +2, because when x is +2, the function value is also 0. We can also say that for f of -1, when x is -1, the function value is -1, and that's the same as f of +1, because when x is +1, the function value is also -1. So, therefore, we can say that this function is even. In part E, does f have an inverse function? Well, in order for f to have an inverse function, it has to be 1-to-1. And the way that we can determine whether or not it's 1-to-1 is to see if it passes the horizontal line test. In other words, if we pass a horizontal line through the graph, if it touches the graph at more than one point at any place on the graph, then it does not pass the horizontal line test. And you could see we could draw a horizontal line here, and it could pass through 2 points on the graph. So it fails the horizontal line test, so therefore it does not have an inverse. The answer is no to part E. In F, is f of 0 a relative maximum, a relative minimum, or neither? Well, notice f of 0 is corresponding to the point -2, right here. So we see that to the left of -2, the function is decreasing, and to the right of -2, the function is increasing. So we can say that it is a relative minimum at f of 0. Let's move on to part G. We want to use the graph of y equals f of x to graph a new graph, g of x. And this is just a transformation. It's f of x plus 1 minus 1. So what does this really mean? Anytime we have a transformation and we have a shift in the horizontal direction, it's connected with the x. So this shift right here in the horizontal direction really is a shift 1 unit left. I know it says x plus 1, but we need to think about it as x minus negative 1. In other words, if it says x plus 1, it's a shift 1 unit to the left. If it had said x minus 1, it would have been a shift 1 unit to the right. We also have a vertical shift right here with this negative 1. In this case, this is a vertical shift, and it is 1 unit down, just like it says. So therefore, what does that mean? For every one of these original points on the graph, I'm going to shift it 1 unit to the left and 1 unit down, and that will be my new graph. Let's start with this point here, negative 2, 0. 1 unit left and 1 unit down is my new point. Let's start with negative 1, negative 1. 1 unit left, 1 unit down. Again, 1 unit left, 1 unit down. I'm over here on 1, negative 1. I shift 1 unit left, 1 unit down. And at 2, 0, I shift 1 unit left, 1 unit down. And here in red is a picture of the transformation, which represents the graph of g of x. Let's move on to part H. Again, we want to use our original graph of y equals f of x to graph a new function, h of x. In this case, h of x is equal to 1/2 f of 1/2 x. So again, we have some sort of a transformation. In this case, this 1/2 in front of our function represents a vertical shrink. In other words, we're going to take each y coordinate and we're just going to multiply it by 1/2. Inside the parentheses, this 1/2 x really represents a horizontal stretch. In other words, we're going to take each of the x coordinates and divide it by 1/2, which is the same as multiplying it by 2. Now, I'm just going to write a little side note so you can remember what to do for the vertical shrink or stretch and a horizontal shrink or stretch. The number in front of the function represents a vertical, either stretch or a shrink. If it's a stretch, we say that this coefficient in front of the function a is larger than 1. If it's a shrink, we say that 0 is less than a is less than 1. So a is between 0 and 1. That's why we have 1/2 representing a vertical shrink in this case. Now, inside the parentheses in the horizontal mode, it kind of works in the opposite manner. If we have the number greater, the number a, the coefficient greater than 1, that really represents a shrink. And it's a stretch if 0 is less than a is less than 1. So let's go ahead and plot the new graph h of x. We need to take each coordinate and do the vertical shrink and the horizontal stretch to find the new coordinate. So let's start with the point -2, 0. Well, the vertical shrink, remember, we multiply each y coordinate by 1/2. 0 times 1/2 is still 0, so the y coordinate doesn't move. For the x coordinate, we have a horizontal stretch. We're going to multiply each x coordinate by 2. Since negative 2 times 2 is negative 4, we move this point over to negative 4, comma 0 and plot that. Next, let's move to the coordinate negative 1, comma negative 1. Again, let's do the y-coordinate first, and let's do the vertical shrink. For the y-coordinate of negative 1, we multiply it by 1/2, and we get a y-coordinate of negative 1/2. For the x-coordinate of negative 1, we multiply it by 2, and we get an x-coordinate of negative 2. The second point is now negative 2, comma negative 1/2. Let's take this coordinate down here, 0, negative 2. Taking the y-coordinate, and I'm taking half of it, that gives me negative 1. And then negative 1, 0, comma negative 1 has an x-coordinate of 0. When I multiply that x-coordinate of 0 by 2, I still get 0. So we can see what's happening. The same thing is going to happen on the other side. And this is what our transformation looks like. Now let's move on to part I. In part I, again, we want to use the original graph y equals f of x to graph our new function r of x, which is negative f of negative x plus 1. Well, this negative out in front of the function right here, this negative really means that we reflect about the x-axis. The negative x inside of the function says that we reflect about the y-axis. And this plus 1, remember, indicates that we have a movement or a vertical shift of 1. So we move up 1 unit. So let's go ahead and do that. Let's take each coordinate, reflect it about the x-axis, then about the y-axis, and then up 1 unit. So let's start with negative 2, 0. When I reflect it about the x-axis, I end up still at the same place because it's on the x-axis. When I reflect about the y-axis, I end over here on the other side, and when I move up 1 unit, it goes up right here. Let's do that again now with the point negative 1, negative 1. Let's reflect about the x-axis, so I'll come over here, and then about the y-axis, I'll come right here, and then up 1 unit. Here we go again. 0, negative 2. First I'll reflect about the x-axis, right here. About the y-axis, I don't need to reflect about the y-axis, sorry, right here. And then, because I'm on the y-axis, and then I move up 1 unit. So here's what my graph is looking like. By symmetry, it will look like this on the other side. So this new graph represents r of x. Let's move on to J. We want to find the average rate of change of the function f from x sub 1 equals negative 2 to x sub 2 equals 1. Remember, average rate of change is really just another way of saying slope. And remember, slope is just given by the difference of the y-coordinates, which is f of x sub 2 minus f of x sub 1. That's another function way of representing the y-coordinates, over the difference of the x-coordinates, x sub 2 minus x sub 1. Well, let's see. We know the value of x sub 2. We also know the value of x sub 1. In order to calculate this average rate of change, we need to find f of x sub 2 and f of x sub 1 as well. So let's make note of those down here. F of x sub 2 is really asking, what's the function value at x sub 2? Well, x sub 2 is equal to 1, so we're really saying f of x sub 2 is equal to f of 1. What's the function value at 1? When x is 1, the function value is down here at negative 1. So we're going to substitute negative 1 in for f of x sub 2. Let's also find f of x sub 1 before we start the problem. f of x sub 1 is really f of negative 2, since x sub 1 is equal to negative 2. What is the function value at negative 2? When we go over here, when x is negative 2, the function value, or the y value, is just 0. So now we have 4 different values that we're going to put into our equation up here. Our slope is going to be f of x sub 2, right here, which was negative 1, minus f of x sub 1, which we found out was 0, over x sub 2, which was 1, minus x sub 1, which was negative 2. And this simplifies to negative 1/3. So our average rate of change from x1 to x2 was negative 1/3.